Or you want that? No, I'll pass them out to you guys at the end. I only wrote it out for the seniors. I just didn't want you guys to be working on it while we're going through this. I will talk about it when we get there. We're going to do the definition, our example built in, 3 more examples, and then I'll tell you what that is. Okay. So what we have up here on the screen, this is called Descartes' rule of signs, which sounds bougie. I promise it is not that big a deal. Like, it is not super duper hard. It's just invented by a French dude named Descartes. That's all it is. That's his name. So this is like Bob's rule of signs. So it's just his name. And so what it is this is a way to figure out how many positive real roots there are and how many negative real roots there are in any polynomial based on what we can see in the equation. So we get positive real zeros, so meaning positive roots like 2, 3, 7, positive 1/2, give me fraction still, is equal to the number of variations of signs. So what we're going to do is we count how many times the sign changes in our equation. So the sign meaning the plus or the minus. So in this example, f of x right here, I've got positive x to the 5th. And then it changes to be a minus sign here. So that's one sign change. Then I have the minus sign changes to a plus. And I have another sign change. The plus again changes to a minus sign, so I have another sign change. Then it changes to a plus again, so there's another sign change. And then it changes to a minus again, so there's another sign change. So this has 5 changes to the sign. You can see that, how it changes sign each time? So we have 5 sign changes. Which means when we're looking for our roots for our polynomial, we can have up to 5 positive real roots. Or it could be less than that by an even integer. So it could be 5 positive real roots, or it could be 3 positive real roots because we count down by 2s, or it could be 1 positive real root. So our positive real roots, we could have 5 of them, or we could have 3 of them, or we could have 1 of them. It's very similar for finding our negative roots, but we have to do a substitution first. If we substitute in the opposite of x into our function, so what I'm going to do is we're going to take our f of x, and I'm going to find f of minus x. So substituting in the opposite of x, and I'm going to write the whole thing out, and then we'll simplify it and see what happens there. So we're going to have minus x to the 5th minus the opposite of x to the 4th plus the opposite of x, opposite of x cubed minus the opposite of x squared plus the opposite of x minus 1. And then we come through and simplify this, getting rid of all those parentheses. So we're seeing what happens to signs here. Our f of minus x, for this first term here, is our negative sign going to hang out or is it going to disappear? Hang out. It's going to hang out. This is the same thing as the opposite of x to the 5th. How about on our x to the 4th? Is this going to hang out or disappear? It's got an even exponent here. So the one that's inside disappears. Because negative 2 to the 4th would still be a positive value. So it's going to be minus, wrong color, minus x to the 4th. How about on our opposite of x cubed? Is that minus sign going to stay or go away? It's going to stay. And since this was a plus over here, this now becomes minus x cubed. How about on our x squared? The one inside disappears, so we just have the one that's outside. So we're going to have our minus x squared minus x minus 1. So how many times does the sign change in the opposite of x? None. It starts as a negative and it stays as minus sign the whole dang time. There are no sign changes. So we know for sure, guaranteed fact, there are no negative real roots. Because there are no sign changes on the opposite of x, we have no negative real roots. So this is going to come into play when we start looking at finding our real roots, because we're going to wind up with lists of options, and this will help narrow down how many of them we have to look for. So what we're going to be doing as we're looking through these examples today is we're going to figure out how many sign changes there are, and we're going to make a list of options we can have. It's going to look like a little table, but that's all we're doing with it, is figuring out how many real positive roots and how many real negative roots we're going to have, which will let us know how many imaginary roots we could have. Okay. Questions on the definition part? The Descartes rule of sign sounds super bougie, but it's literally count how many times your sign changes. Okay. So this will be how the questions get worded. It says use Descartes' rule of signs to determine the number of positive, negative, and non-real solutions we have to the equation. So we get our positive real roots by counting. That is not how we spell real. There we go. Or how we spell root. I'm so good at braining today. So we're going to count how many times our sign changes here. So how many times does our sign change here? Yeah, so we're starting positive, and then it switches to negative. So there's 1, 2, 3. So we have, at most, 3 positive real roots. Or we could have 1 positive real root, because we're going to count down by evens. Or we count down by 2s. Because it's always going to be like counting down by 2. I'm trying to figure out the other way to word that. It's less than that by an even integer. So 3 minus 2 is how we get the 1. So we're going to just subtract 2 every time until we get down to 1. 1's always going to be our last option. It's either going to be 1 or 0. So then to find our negative real roots, we need to substitute in that opposite of x. So we're going to do our f of the opposite of x and see what happens to our signs here. So our opposite of x cubed minus 6 opposite of x squared plus opposite of x minus 3. This is how we see our negative real roots. So we're going to simplify these, and then we're going to count our sign changes. So, yeah, on our cube, odd degreed pieces, our negatives hang around. So negative x cubed is the same thing as negative 4 x cubed. On our even degreed pieces, the negative inside our exponent cancels out, because negative x times negative x, that's positive x squared. So this sign's going to stay the same, minus 6 x squared. On our minus x, that's x to the first. That means it's an odd degree. Therefore, this negative sign hangs around, so we have our minus x. And then we have minus 3. So how many sign changes do we have in this part? I have no sign changes. We start negative and we ended negative. But there was no plus in between here. So we have no changes. So how many negative roots do we have? Zeros. This is 4.3. So we have 0 negative real roots. What is the degree of the function? 3. So how many roots is this function going to have? 3. So what we're going to do to figure out how many imaginary roots we could have is I make a little table down here. Where I'm going to talk about my positive roots, my negative roots, my imaginary. That winds up at our total. So if I have 3 real roots and 0 negative roots, how many imaginary roots is it going to have to get to the total we need? 0, because we should have a total of 3, because that's our degree. Ooh, that is not the color I meant. I meant to grab a gray, not a fluorescent orange. So, if I have 1 real root, I still know I have 0 negative roots because we can't have any. How many imaginary roots are we going to have to get to the total we need? Yeah, so we would have to have 2 imaginary roots to get to the total we need because we have to have 3 roots. So we either have 3 real roots or we have 1 real root and 2 imaginary roots. And a really quick way to kind of spot check this is imaginary roots always, always, always come in pairs. You should never wind up with a 1 in your imaginary section. Never, ever. Imaginary roots always come in pairs. Okay? So this is the piece that we're going to be building for all of our examples today. We're making this little table with our list of options. It doesn't give us what the roots are, just how many of each type. Okay. And we're going to practice this a couple more times. But questions on this one? Okay. Same vibe. We're using our Descartes rule of sign to determine the number of positive, negative, and complex answers for this polynomial. So our first step is to find our number of positive roots. How many sign changes do we have for the positive version? Same. Let's do it. So I started positive, so we've changed to negative here, so there's 1. Switches to a plus here, so that's 2. And then the next time it changes isn't until all the way over here. So 3, and then it's negative to the end. So how many positive real roots are we going to have? 3 or 1. So then we need to do the same thing for our negative. So we're going to do our f of the opposite of x. So substituting that in. And as you get a little bit more practice with this, if you can do this simplification without writing it in as substitution first, I'm 100% okay with that. That is the problem with writing and talking at the same time. I'm mixing pieces up. So if you can do this simplification without writing it down, I'm totally okay with that. But if you want to do this as a substitution and then simplify, that is also okay. I'm going to run into my numbers. Opposite of x, minus 3. So we're substituting in that opposite of x for every single one of these. So when we do this, my opposite of x to the 7th, that's an odd degree, so my negative sign stays. So this is negative 3x to the 7th minus 4, my opposite of x to the 4th, that's an even degree, so that sign just kind of disappears. So we have x to the 4th. My 3 opposite of x cubed, that's an odd degree function, so that is negative 3x cubed. Our sign hangs around. Then we have our 2 opposite of x squared. Opposite of x squared, that opposite cancels out. So we're going to have our positive 2x squared minus the opposite of x becomes plus x. And then we have minus 3. Questions on that part? Because that tends to be the place where we trip up most. All right, so how many sign changes do we have here? 2. Because we start negative, and then we switch to positive here, and then we switch to negative here. So we have for our negative roots, negative real roots, we have 2 or 0. Because we count down by 2s. So I can have no negative real roots. It's entirely possible for me to have none of them. I don't have to have one. I could have 2. What is our degree of our equation? 7. So how many roots do we need to have? 7. So with some combination of positive roots, negative roots, and imaginary roots, we gonna have a lot of options here. So we're gonna have some number of positive roots. We're gonna have some number of negative roots. We're gonna have some number of imaginary roots. And no matter what, I need it to total up to 7. All of them need to total up to 7. So if I have 3 positive roots and 2 negative roots, how many imaginary roots would I need to have? 2. If I have 3 positive roots and no negative roots, how many imaginary roots do I need to have? 4. If I have 1 positive root and 2 negative roots, how many imaginary roots am I going to need? 4. And then our last one here, if I have 1 positive root and no negative roots, how many imaginary roots are we going to have? 6. So I could have any of these combinations. These are different setups we could have. Okay. Questions on this one? Okay. Because we're going to do one more example like this. All right, I want you guys to try this one. See what you can get. Yes, dear.
So it says it could be like 1 positive root.
Mm-hmm.
So that means like, is there a way that we could use 0 positive?
Nope, because we always count down by even, so it would have to have 1 positive real root. which is going to be really handy when we look at stuff next week. That'll be really helpful for us because we're going to have to figure out what that root is.
I really like driving around in the car.
That is quite fun.
That was what I actually liked.
It's also really fun to just school on some like 12-year-olds.
And we actually got a big
plays Fortnite.
I am in fact the Fortnite coach for the esports team. Oh snap! Yep, we have game tonight. Yeah, it's Zone Wars this year, so it's 4v4 v4v4. But I don't know who we're against yet tonight. But our Smash Bros team is also competing tonight too. So
That's kind of cool.
yeah, yeah. I was like, I can look at who we're competing. Smash Bros, I know who we're competing, but I just don't know off the top of my head.
I've been into I've been playing that all the time. I'm not.
We have a lot of people that play on our Smash team.
Did I play at school?
Yeah.
On what?
Smash plays on Switch. The Fortnite, we have some PCs that we play on in K103, Mr. Russell's room. Let's see.
And my Joy-Cons, whenever like I tried to play like this, they like slide up.
We're against Franklin Central tonight in Smash Bros. Okay. So what do we get? How many positive roots are we going to have? 1. How many negative roots are we going to have? 3 or 1. So what is our total? How many do we need to have? We need to have how many total roots? 4 total roots. So we have one set that could have how many imaginary roots? 0. And we have one set that would need to have 2. No matter what, we're going to wind up with a total of 4. How did I lose you, David? Or where did I lose you, David? What's up? This is not on the quiz for Friday. Do you see it? Because there's 3 sign changes, and then we count down. So we subtract 2 until we get down to 1 or 0. Because it could be 3 or it could be 1. Just like when we had, where was the one that had lots? The first one. We had 5, or it could be 3, or it could be 1. Because it's less than that number by an even integer. So we subtract 2. So if we had 4 sign changes, it would be 4 or 2 or 0. So it's always going to be subtract 2 until we get down to 1 or 0. Every single time. And that's just one of those things we have to kind of like practice. Okay? Questions on that bit? Okay. So we are schedule-wise, honestly, in a really good place. So what I have and what this paper that I had our seniors pick up is a review for the quiz on Friday.
Oh my, you did a review for us. Thank you.
I promise it is longer than the quiz. Do not panic by the sheer number on here. Okay? Because I gave you couple of versions of each kind of question. Okay? So this is what we use in the quiz. I will get the answer key for it put up by the end of the day today. Just so you guys can like check your answers and stuff. But honestly, I did just enough of it to make sure that the questions functioned. I didn't make it pretty. So I will write the key properly pretty. Probably in fifth period today. But the one I have is kind of scribbled out several times because I had to fix a few of the questions. Okay, but that is it for today. So we have PSAT tomorrow, and then we have quiz 7 on Friday. It's over set our limits, 4.1 and 4.2. So it's covered. Everything on this review is covered on the quiz. So make sure we can do all these things. And you guys have the next almost 15 minutes where you can either work on some of the homeworks or you can work on this review. What's that? That would be a root, a factor. It's an imaginary one. We did one like that, I think yesterday, where they always come in pairs, so it's always going to be plus or minus 3i. Where? What happened to your x's? Where's the x's in those factors? And it's not 3 plus I, it's just 3i.
But don't
This
you
can this be for points, for completion points?
Yeah. Always is. Yeah, I'll give you points for it. Turn it in on Friday. I'll give you points for it.
So it would just
So build it the same way. But then we don't want to have i's in our polynomials, so we need to multiply that for it. So you took these numbers, the 4, and you did what with it? X minus 4. Why are you treating this guy differently? Yeah.
so it would be x
Uh-huh.
minus.
Uh-huh. And they always come in pairs, so
Oh, I have to do x.
uh-huh.
Oh.
Then multiply those two pieces together because we don't leave i's in our polynomial.
Oh.
What's that?
How am I supposed to know?
Where'd your I go? Where'd the I go?
Sorry, I forgot.
You gotta keep the I.
I forgot about that.
And then we gotta multiply those pieces together because we don't leave i's in polynomials. So we multiply those chunks to get it back to be.
I did the first one. Like I.
We can leave the first two as factor form because it says factor form anyway, but we just don't have i's in our factors because that's it. So use this time, work together if you guys want to. Totally cool, but kind of chill today.